Hi everyone, my name is Michael. I'm going to be solving question number 2. In this question, we have a spherical shell with radius r, which has a uniform surface charge density sigma and is spinning around its axis with an angular velocity omega in the z-hat direction. The first thing we need to find is the surface current density k. The surface current density k is equal to the surface charge density times the velocity vector. The velocity vector we know is equal to omega cross r, which equals r omega sine theta in the phi hat direction. Putting these all together, we get k equals sigma r omega sine theta in the phi hat direction. Next, we would like to find the magnetic dipole moment m. M we know equals the current I times the vectorial area. We also know that k equals di over dl perpendicular. So if we rearrange that a little bit, we get I equals the integral of k dl. We can see with a little graphic here that dl perpendicular equals the radius times d theta, which makes I equal to the integral of k r d theta. Next, we need to find the area vector, which is essentially just the area of each slice of the sphere that we're concerned with. And the radius of each of those circles will be equal to the radius of the sphere times sine theta, depending on how high they are up the sphere. This gives us the total integral for the magnetic dipole moment, evaluated from 0 to pi. And taking all of the constants out of the integral and integrating sine cubed theta d theta from 0 to pi, we get 4/3 pi sigma omega r in the z-hat direction. Next, we want to find the leading order contribution to the magnetic vector potential at a point r theta phi, where r is much, much greater than the radius of the sphere. Here we have the equation for the magnetic vector potential, which is equal to mu naught over 4 pi times the magnetic moment crossed with r hat divided by r squared. Now we can find m cross r hat equals m sine theta in the phi hat direction. And combining those and crossing out a few terms, we can see that the magnetic vector potential is mu naught sigma omega sine theta over 3 times the radius of the sphere to the 4th divided by r squared in the phi hat direction. And for r is much, much greater than the radius of the sphere, that magnetic vector potential will go to 0. Next, we'd like to find the leading order contribution to the magnetic field at a point r theta phi, where r is much, much greater than the radius of the sphere. Here I'm taking the curl of the magnetic vector potential in spherical coordinates, so I've already gotten rid of all of the terms that don't matter. Evaluating for the r hat component, we get a couple of signs that cross out. Evaluating in the theta hat direction, we get a very similar answer, except we get a sine instead of a cosine. And combining them together into one vector, we get the magnetic field is equal to mu naught sigma omega radius of the sphere to the 4th divided by 3r cubed. And in the r hat direction, that's multiplied by 2 cosine theta. In the theta direction, that's multiplied by sine theta. And last but not least, I'm going to make a rough sketch of the magnetic field in the zy plane. Here we see that we have magnetic field lines extending up from the top or north pole and going down and around to the south pole of the sphere. You may notice that this looks a lot like the magnetic field of the Earth. And in fact, the Earth can be approximated pretty well by a spherical shell like this one. Understanding the physics of a problem like this one can give us pretty good insight into the magnetic field of the Earth, which shields us from harmful cosmic rays from the sun. And as a recap, we can look back up here at the top and note that in this problem, we studied a rotating spherical shell with surface charge density sigma. We were able to find the surface current density K. Using that, we were able to find the magnetic dipole moment. Using the magnetic dipole moment, we were able to find the magnetic vector potential of the sphere. And by taking the curl of the magnetic vector potential, we were able to find the magnetic field of this shell.